Hi everybody. In this video I'm going to go through a bunch of Exam 1 practice problems and solutions for probability and statistics. This course happens to be calculus based, but many of these problems do not require calculus, so you can still get benefit out of it even if you don't know calculus. The problem types run the gamut from, as you can see here, basic laws of probability problems. We'll use a Venn diagram to help us solve this one. Combinatorial probability, where we need to use combinations and perhaps permutations. We also get into, for example, laws of probability like the independence rule, Bayes' theorem. We get into discrete and a little bit with continuous random variables, particular random variables like binomial, Poisson, and exponential. So let's go ahead and get started. You can see in problem 1, we are supposing that we've got some information here. The probability of A union B, meaning A or B, is 0.6. The probability of the complement of A is 0.6. And the probability of A intersect the complement of B is 0.3. Our goal is to find the probability of A intersect B, showing our work, circling our final answer. Now, it's tempting to look at a problem like this and say, okay, what formulas do I need to use? However, in this kind of situation, it really is best to probably try a Venn diagram first, and I think that's really the way to go here. So draw a box. This rectangle, represents the sample space. And it doesn't look like a very good rectangle there. Draw a couple of circles that are overlapping, representing the events A and B, okay? And see if you can fill in numbers in these 4 spots here, here, and here, representing the probabilities of each of these sectors individually. The probability associated with this part, this crescent moon shape, would be for A intersect the complement of B. That's outside of B. Over here, this crescent moon shape, it would be B intersect the complement of A. This part in here would be A intersect B, which is what we're after over here, and out here would be the complement of A union B. Start filling in numbers if you can. I'm going to search and see if I can fill in one of the numbers that would go with one of these 4 spots right away, and in fact I see this one. The probability of A intersect the complement of B is 0.3. That's a number that can go right here right away, and that's good. These 2 numbers cannot be filled in right away, but maybe with a little bit of algebra and perhaps some guesswork, I can quickly figure them out. And I can also hopefully figure out the answer to the question, the probability of A intersect B, which I'm going to represent with the letter X. Call this X, call this Y, call this Z, and then write down some equations that you know have to be true based on the laws of probability. For example, the sum of all the probabilities has to equal 1, so 0.3 plus X plus Y plus Z equals 1, and therefore you can quickly say that X plus Y plus Z is 1 minus 0.3, which is 0.7. You also know that the probability of A union B is 0.6. Therefore, 0.3 plus X plus Y equals 0.6. And therefore, X plus Y equals 0.6 minus 0.3. X plus Y is 0.3. We haven't used this bit of information yet. The probability of the complement of A is 0.6. That's everything outside of A. Y plus Z will be 2 probabilities that will add to the probability of the complement of A is 0.6. Okay? What's our goal? Again, is to find this. That is represented by the letter X. I can pretty quickly solve it, looks like. For example, I can take this equation and this equation, replace the Y plus Z in this equation with 0.6. So I get X plus 0.6 equals 0.7. Therefore, X equals 0.1. 0.7 minus 0.6, and that is the probability that I'm after. That is the probability of A intersect B. You may want to just double check your work by perhaps finding the values of Y and Z if you can as well. For example, this equation, just see if everything is consistent. This equation would imply, based on this one as well, that Y is 0.3 minus 0.1 is 0.2, and that I could combine this equation and that one to say that Z is 0.4. Is everything consistent? Do all the probabilities add to 1? 0.1 plus 0.2 plus 0.4 is 0.7, plus the 0.3 right there is indeed 1. It does look like everything is consistent, but the answer to the question is the value of X. The probability of A intersect B is 0.1. Okay? And I didn't really use the laws in their more abstract form. I'm thinking about trying to solve this as quickly as I can based on a diagram, and the diagram really helps you understand it pretty quickly. All right, on to this problem. Number 2, a contractor has 9 suppliers from which to purchase tools. She will select 4 of these at random and ask each supplier to submit a project bid. Okay, so it's this woman doing the collecting of these different suppliers that she wants to purchase tools from them. Part A, in how many ways, so this is a combination and or permutation problem, can the selection of bidders be made? And if your firm is one of the 9 suppliers, saying your firm, what is the probability? So we have to calculate a probability as well that you will get the opportunity to bid on the project. Okay? So I always find these problems a little bit tricky. You need to really think carefully here. First of all, let's look at part A. In how many ways can the selection of bidders be made? Not thinking about giving favoritism, for example. We're not thinking about probability at the moment. We're just trying to enumerate the possibilities. We have 9 suppliers to choose from, and we're selecting 4 of them. Evidently, based on the way this is phrased, the order that we choose them in doesn't matter. Therefore, this is not a permutation problem. This is a combination problem. The answer to part A is 9 choose 4. In alternative notation, you can write it like this. 9 choose 4. That is not 9 divided by 4. It's 9 choose 4. The formula for combinations would say this is the number of suppliers, in this case, factorial, divided by the number of that you're selecting, 4 factorial, times 9 minus 4 factorial, which of course is 5 factorial. You can use your calculator, and in fact, I let my students use a calculator here if they want, although I might ask them to show all the details, and it is kind of fun, actually, to show all the details. For example, 9 factorial is 9 times 8 times 7 times 6 times 5 factorial. That can cancel with the 5 factorial there. What is 4 factorial? It's 4 times 3 times 2 times 1. These are going to divide out, leaving me with 9 times 8 times 7 times 6, all divided by 4 times 3 times 2 times 1. Have a little fun with it. Go ahead and do some more cancellation. The 4 cancels with the 8 to leave a 2. That 2 cancels with this 2 to leave a 1. This 3 cancels with either the 6 or 9. Let's cancel it with the 9 to leave a 3. So it looks like we're left with 3 times 7 times 6, 21 times 6, and that will be what? 126 is the value of 9 choose 4. Let's just double check it with a calculator. And if I didn't ask my students to actually show that work, they could just use their calculator straight away. On a TI-84, if I type 9, then go to the math mode and go over to probability, which I could have gone backwards with, and go down to NCR. I press that and then go 4. And yes, 126 is the value of 9 choose 4, and that would be the answer to part A. On to part B. What is the probability that your firm gets the opportunity to bid on the project? Okay, now this might seem like it's pretty tricky, pretty hard, and I think if you think about it systematically, it is. Turns out the answer is pretty simple, but let's see if we can be systematic, and let's in fact do it in 2 ways. Okay, first of all, let's go ahead and do it directly. How do you figure out the probability that you will get the opportunity, your company, you are a supplier, to bid on the project? What you want to do, again, this is the total number of ways of choosing 4 suppliers out of these 9. You want to think about how many ways there are choosing 3 out of 8, because you're pretending you are one of the ones that has already been selected. If we can figure out 8 choose 3, then the ratio of 8 choose 3 divided by 9 choose 4 should be the answer. You got that? Again, you're pretending that you have been chosen. You're trying to think about how many groups of 4 out of 9 are there where you are one of the ones chosen. So pretend you've been chosen. Then there are 8 suppliers left to choose from, and you're going to choose 3 of them because 1, you have already been selected. 8 choose 3. In terms of factorials, that's going to be 8 factorial divided by 3 factorial times 5 factorial. That'll be 8 times 7 times 6 times 5 factorial, all divided by 3 times 2 times 1 times 5 factorial. The 5 factorials will cancel. 3 times 2 times 1 is 6. That cancels with this 6. Looks like we're left with 56 for the answer of the number of groups of 4 of which you are one of them, and therefore the probability that you will get the opportunity to bid looks like it's the ratio assuming these are equally likely, 56 divided by 126, that's the same as 28 divided by 63. Both of those are divisible by 7. That's the same as 4/9. And look at that, 4/9, that's the same as the number selected divided by the number of suppliers. However, I really think you should go ahead and go through a derivation like this to really confirm that it is that simple in the end. It's not necessarily obvious that it was going to turn out that simple. Let's do this problem in one more way that would be instructive as well. Let's first find the probability that you will not get the opportunity to bid. And then we'll take, which will evidently be 5/9, because to get the final answer, we'll take 1 minus that. So what's the probability that you will not get the opportunity to bid? Think of it as a stepwise manner. We're going to use conditional probability here, and that's why I wanted to do it as well. First of all, what's the probability? Not getting to bid means you're not the first supplier chosen, and you're not the second, and you're not the third, and you're not the fourth. Connecting with the word "and" there, we can multiply the probabilities, but they're conditional probabilities. These are not independent. When there's 9 suppliers to begin with and you're choosing the first one, you have an 8 out of 9 chance of not being chosen. The conditional probability that you are not chosen in the second step of choosing the second one is 7 out of 8. The conditional probability of not being chosen the third choice is 6 out of 7. And the conditional probability of not being chosen for the fourth supplier is 5 out of 6. And lo and behold, a bunch of stuff cancels here. You're left with 5/9, and then the answer that we're after is 1 minus 5/9, which is 4/9. Okay, so it's nice to see this work out in a couple different ways. I think it's, again, not completely obvious that the answer would have been 4/9 to begin with. It does work out nicely in this particular kind of problem, but be careful in general. Sometimes these problems don't work out so nicely. All right, we're on to the next problem, which is also combinatorial. I feel like you can never get quite enough practice with these combinatorial problems. We've got 6 soccer players and 5 football players. Okay, I am in the United States of America, and to us, soccer is what everybody else calls football, and football is American football. And we have 11 people that are 6 soccer players and 5 football players that are on a bus. Okay, but we're going to take some people off the bus. We're going to choose a group consisting of 3 soccer players and 2 football players chosen from this group. Show the details of your work to figure out how many ways that can be done. Okay, so we are choosing without respect to order, so this is a combination problem again, but it's also a problem where you want to think of this in 2 steps, because you got these 2 different groups of people, soccer players and football players, and you're choosing from both groups. You want to sort of imagine maybe choosing the soccer players first and then choosing the football players. That would be a fine way to do it, to help ultimately use also the fundamental counting rule to multiply the combinations to get the total number of possibilities. Here's what I mean. Okay, that was a mouthful. First, choose the soccer players. There are 6 choose 3 ways to do that. Then choose the football players. There are 5 choose 2 ways to do that. Altogether, you would multiply those 2 numbers to get the final answer for the first question here for part A. Okay, these are quick enough to do by hand, maybe even just in your head. The 6 factorial here will cancel. We'll have a 6 times 5 times 4 times 3 factorial, and that will cancel with one of those. And 3 factorial down there is 6, which cancels with that 6. This is a 20 here. And then with 5 factorial, that's 5 times 4 times 3 factorial. Cancel the 3 factorials. You have 20 divided by 2 factorial, which is 20 divided by 2, which is 10. 20 times 10 is 200. The answer to part A is 200. That's the ways you can get groups of 3 soccer players out of 6 and 2 football players out of 5. Part B, find a probability that a group of 5 players selected at random from these 11 people on the bus will consist of exactly 3 soccer players and 2 football players. Okay, so you think about it here. this was our number of ways of choosing 3 soccer players out of 6 and 2 football players out of 5. If we're going to use that to figure out a probability of getting that exact kind of group of 5 people, we are also going to need to know the total ways of getting 5 people out of a group of 11. Does that make sense? Where you might have maybe 4 soccer players and 1 football player, 5 soccer players and 0 football players, 2 soccer players and 3 football players, etc. You don't have to think about the breakdown in terms of soccer and football players. You can just say I have 11 people and I'm choosing 5 of them to figure out the denominator for the probability. So that's 11 factorial divided by 5 factorial times 6 factorial. Again, you should feel comfortable doing that without technology, or at least doing some factoring for fun, but let's go ahead and just use the technology here. 11, go to math mode, choose 5. That's 462. That's not the final answer. We are after a probability, so we need to do the ratio. The probability of this thing here, where you've got 3 soccer players and 2 football players, is going to be the ratio 200 divided by 462. That's the same as 100 divided by 231. And it looks like that cannot be reduced anymore. One approximation, 100 divided by 231. And get it to 4 places after the decimal as is requested here. It looks like it's going to be 0.4329. Okay? The fraction is the exact answer. The decimal is an approximation. Though you're thinking about it in terms of real-life approximations, well, in this case, this is the exact, but in many situations you have to round to a certain number of significant digits. We're not worrying about that here. Number 4, a softball player has a batting average of 300 is what you say here, which means she gets a hit in 30% of her official at-bats. So by official, you're ignoring getting a walk, that kind of thing. Suppose she gets 6 official at-bats during a long extra inning game. What is the probability that she got 2 hits? Assume the at-bats are identical and independent. Okay? You can try to figure this out using basic principles, using ultimately the addition rule for mutually exclusive events, and also the multiplication rule for independent events. However, that's quite a bit of work, okay, because there are lots of ways of getting 2 hits in 6 at-bats. You could get the first 2 at-bats, you could get hits, and the next 4 you could not get a hit. You could get hits on, say, the second and 5th at-bats and not the other ones. There are lots of ways it can happen. So trying to derive this from scratch is not so nice. Instead, what you want to do is you want to recognize we should use a particular kind of binomial, a random variable. It's a binomial random variable is the answer. Because we're counting, we're going to let capital X be the number of successes, in this case, number of hits, in 6 at-bats. So we have a fixed number of trials, 6. The probability of success on each trial, which is each at-bat, is the same because the trials are identical and independent. So we know this is a binomial random variable, and therefore we can use a formula that says the probability that capital X equals a particular number, call it little x, is n choose little x, where n is the number of trials, and 6 in this case, times the probability of success raised to the little x power, because we're having little x successes, times 1 minus the probability of success, which is the probability of failure, to the n minus x power. X is the number of successes, n minus x would be the number of failures. So you should certainly be able to use this formula if I request you to show your work like this, or if your teacher asks you to show work like this. Here's the way it would look. We're getting 2 successes. Probability of success is 0.3. Probability of failure is 0.7. That would be the calculation to do. This is going to be 6 factorial divided by 2 factorial times 4 factorial. Let's go ahead and just write down what these things are. 0.3 squared, of course, is 0.09. 0.7 to the 4th is not so easy to do in your head. 0.7 to the 4th power is 0.2401. This product right there is 0.021609. What is this? That'll be 6 factorial. 6 times 5 times 4 factorial. The 4 factorials cancel. You're ultimately going to divide 6 times 5 divided by 2. 30 divided by 2 is 15. And so we need to multiply this number by 15 to get the final answer. Our probability is about 0.324. Let's just round it to that. 0.324 chance that she gets 2 hits out of 6 at-bats, okay? Which is not surprising that that should be relatively high. With a 300 average, her expected value, this is not requested in the problem, for a binomial random variable is n times p, which makes good intuitive sense. If she gets 6 at-bats and her probability of success on each at-bat is 0.3, you would expect 1.8 successes out of 6 at-bats. Of course, that can't literally happen. This is a long-run average. But 1.8 is 30% of 6. 2 is 33% of 6. Those percentages are fairly close. You should expect a fairly high probability here. Okay. The next problem is a type of problem I ask a lot. It's a disease testing. And okay, we're talking about COVID-19 here, everybody's favorite disease. Not, okay? Suppose 1.2% of the population tests positive for the coronavirus causing the disease COVID-19, at a particular moment in time. But there's a new test that's come on the market that they're testing to see how accurate it is. It's a new test. And in people that are known to have the virus, it comes back positive correctly, saying they have the virus 98% of the time. In people who are known to not have the virus, it comes back negative correctly 99% of the time. So it sounds kind of accurate. Okay? These are conditional probabilities. That's the conditional probability of getting a positive test result if it is given that you definitely have the virus, C19. And this is the probability of a negative test result. The complement of positive, I'll call it pos prime, I could also call it neg for negative. Given that you do not have COVID-19, that's 0.99. But that's not what we want to know. We want to know if you take the new test and it comes back positive, saying you have COVID-19, the virus at least, what is the probability that you actually do have the virus? It's not 99%, it's not 98%. Okay, it's something different. I gave them the hint to use Bayes' theorem or a tree diagram to help you solve this, but you should be able to solve it even if you didn't get that hint. We are after the probability that you actually have the disease, the probability that you have the virus, I should say. C19 virus is what I imply by this. It doesn't mean you're necessarily sick. Given that the test comes back positive, that's a different conditional probability than these two. Bayes' theorem is really based on the definition of conditional probabilities plus some more laws of probability. I will write out the formula, but it's nice to draw a tree diagram as well. And the first set of branches represents having the virus for COVID-19 or not having the virus for COVID-19. The second set of branches represents testing positive or not testing positive, in other words, testing negative. Pos and pos prime, the complement of pos. It's good to label the branches in the tree with the corresponding probabilities. One piece of information I haven't dwelled on is the fact that only 1.2% of the population tests positive for the virus by some other test. So the probability associated with having the virus would be 0.012, and the probability with not would be 1 minus 0.012, which would be 0.988. Doing calculations in my head, hopefully don't make a mistake. When it's known you have the virus C19, what is the probability it comes back positive? That's the 98%. This is 0.98. Therefore, this is 0.02. And when you actually do not have it, it comes back negative correctly 99% of the time. This is a 0.99, and this would be then a 0.01. And if you set up the tree diagram this way, you want to put the probabilities of both events happening, the product of these probabilities along each of the branch paths over here. I'm really using the multiplication rule, the general one. There's nothing about independence here. These products are going to involve conditional probabilities. So the probability of having the virus and testing positive is the probability of having the virus times the conditional probability of testing positive given that you have the virus. That's the 0.98 both here and here. I multiply those, and that product, 0.012 times 0.98 is 0.01176. And you're going to do the same kind of products along the other ones. You actually don't need all of them, but I'll do them all anyway. Here it's 0.012 times 0.02. Along this path, it's 0.988 times 0.01, and the biggest product is going to be along this bottom path, 0.988 times 0.99. Let's go ahead and figure out all these anyway. 0.012 times 0.02, first of all, is, that's scientific notation there. If I convert it to decimal notation, that's going to be 0.00024, because it's 2.4 times 10 to the negative 4 power. Okay, I can do this one without calculator. This is going to be 0.00988. And this bottom one, 0.988 times 0.99, is the biggest probability of 0.97812. By the way, these four probabilities, here, 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 and here, should add to 1, but let's not bother. Let's now find the probability that we're after. We'll just, based on this information, we'll just use the definition of conditional probability. The conditional probability of having the virus for COVID-19 when the test is known to come back positive, by definition, is the probability of both having the virus and the test coming back positive, divided by the probability that the test comes back positive. This one right here is this first number up here, 0.01176. This one, Bayes' theorem breaks that apart into the sum of some products of conditional probabilities with ordinary probabilities, in fact, that we get up here. Well, I hope it makes intuitive sense. I'm not going to write it out. That it goes with the numbers that go with the positive result. These two numbers, we need to add up those probabilities. 0.01176 plus 0.00988. Didn't give myself much room here. This is 0.01176 divided by 0.01176 plus 0.00988 is 0.02164. Hopefully no mistakes. I'll try to put a note if there is a mistake. 0.01176 divided by that is about 0.5434 as your approximate probability of actually having the virus when this new test comes back positive. So, and it's possible sometimes in these problems that this probability could even be a lot lower. So, this has practical importance. Just because these probabilities are high doesn't mean when you get a positive test result that you have the virus or have some other disease. Okay, and it's worth getting a second opinion oftentimes, especially when you're using a new test. Number 6, when you play darts, you hit the bullseye with probability of 0.0625 on any given throw. Suppose the throws are identical and independent. Sounds like we're dealing with a random variable here, kind of like the softball. Find the probability that it takes you 10 throws until the first time you hit the bullseye. Show your work. Okay, then once again, just like with the softball one with the binomial random variable, we can either show work from first principles or use a known formula. It's easier to do either one in this case. If I let x be the number of throws until the first time you hit the bullseye. That is not a binomial random variable. From hopefully what you've learned, it's called a geometric random variable when you have a probability of success that stays the same on every trial, in this case every throw, and it's independent of what's happened before, so we can apply the multiplication rule. That's called a geometric random variable when x counts the number of trials until the first success, in this case the first bullseye. All right, and the probability, the general formula that capital X, the random variable, equals the particular number little x, turns out to be, if p is the probability of success, it's 1 minus p to the x minus 1 power, because you're going to have x minus 1 failures. 1 minus p is going to be the probability of failure on any given trial, times 1 success, which has probability p. That would be the formula that we need. That's the general formula for the probability that a geometric random variable, the number of trials till the first success, equals a particular number x. It means you again had x minus 1 failures and 1 success at the very end. So it's the product of those probabilities of failure, x minus 1 times the probability of 1 success at the end. So 1 minus 0.0625, did that in my head, it's 0.9375. Needs to go to the 10 minus 1 power, that's the 9th power, and then 0.0625. That will be the probability that it takes you 10 throws until the first time. So 0.9375 to the 9th power times 0.0625. This is approximately 0.03496. Okay, for the probability that it takes you 10 trials till the first success. Part B asks for the mean expected value, number of attempts until the first time you hit the bullseye. For a geometric random variable where p is the probability of success on any given trial, that mean turns out to be 1 over p, in this case 1 over 0.0625, and that is a nice number. 1 divided by 0.0625 is 16. In fact, 0.0625 is 1/16. We've got a probability of success on any given throw of 1/16. It should make intuitive sense that on average it's going to take you about 16 throws to get your first success. Okay, so hope that makes sense. It's using known formulas for geometric distribution, including probability, the PDF, or PMF for probability mass function, and the mean, the expected value. All right, 2 more pages, 4 more problems. Here we have a discrete random variable with probability density function, also called probability mass function, f of x defined by this table below. For discrete random variables, little f of x is called oftentimes probability mass function. That's really a better name. The book I use calls it still a probability density function. I do think that's better reserved for continuous random variables, because with probability mass functions, or PMFs, it's the value of little f of x that gives you probabilities, whereas with continuous random variables, you have to integrate the discrete density function, or the continuous density function, to find probabilities. All right, part A says fill in the remaining 1 value of f, little f. Part B, fill in the 4 values of the cumulative distribution function, the CDF, capital F of x. In the continuous case, capital F is an antiderivative of little f. This is notation similar to what you see in calculus. Show how to find the mean using the summation formula, the definition of E of x. And part D, find a formula for the moment generating function and confirm your answer to part C by finding that derivative if you know about moment generating functions. So this problem, you may or may not know how to do all of it, but it's all worthwhile. Of course, what goes here, if these are the only possibilities for x, 1, 2, 3, and 4, is going to be 1 minus the sum of these things. I'm going to go ahead and fill in the CDF first, and that'll help me fill in the top number for this number over here for the PDF. So for the CDF, the capital F, I'm just accumulating values of little f. I'm just adding them. So the first value, capital F of 1, just equals little f of 1. Then I need for capital F of 2 to add the value little f of 2 to capital F of 1. The number that goes right there is 0.22 plus 0.35, 0.57. For the next one, I add on 0.28. That'll be 0.85. Hopefully no mistakes. And then these numbers for the PDF or PMF have to add to 1. So far, they've added to 0.85. Therefore, what goes here is 0.15. And what goes right here for the CDF is 1.00. Okay, so that's filling in the table. That's parts A and B. On to part C, show how to find the mean with a summation formula, really the definition of the mean. Part C, the mean, mu, also called the expected value of x. The summation formula looks like this. Sum the values of the products little f of x times, or little x times little f of x over all x where little f of x is positive. So that's going to be 1 times 0.22. That's the first value of x. The second value of x is 2 times the corresponding probability is 0.35 plus the next value of x, 3 times its corresponding probability is 0.28 times the last value of x, 4 times its corresponding probability from the little f of x function, 0.15. So this is 0.22 plus 0.70 plus what would that be, 84 plus 0.60, hoping I don't make any mistakes. That's a 0.92 there, plus that is going to be what, 1.76, plus that is 2.36, hopefully. I better double check. 0.22 plus 0.7 plus 0.84 plus 0.6 is, yes, 2.36 is going to be the mean. As we saw before, the mean doesn't have to be one of the possible values of x. X can only be 1, 2, 3, or 4. It's not a possible value. It's the long-run average value of x. If you did this experiment of many, many times of observing the value of the random variable capital X based on this PDF, its distribution, in the long run, the average of the numbers you get for little x, sometimes 1, sometimes 2, sometimes 3, sometimes 4, would average out close to 2.36. That's part C. On to part D. Find a formula for the moment generating function, which by definition is the expected value of the function e to the tx. And when you compute this, you treat the t as a constant. But ultimately, in the end, after you've done that, you treat the t as a variable. Whether something's a constant or variable is all in your head. It's all in how you're thinking about it. As a summation over all x where little f is positive, this is going to be the sum of these values. So the probabilities are the same as they were in part C. It's these things that are different. First value of x is 1. So this becomes e to the t times the corresponding probability, 0.22, plus next value of x is 2, e to the 2t, replace x with 2, times 0.35. Next value of x is 3, you get e to the 3t times 0.28. And the last value of x is 4, we get e to the 4t times the corresponding probability. Little f of 4 is 0.15. And that actually is the answer. You don't have to bother simplifying it. I mean, we usually put the numbers in front of the e's, of the exponential functions there, but it's fine to leave it like that. What does the moment generating function do? One thing it does is it generates moments. By taking derivatives and plugging in 0, you can find expected value of x, expected value of x squared, expected value of x cubed, etc. So I need to find the derivative of this function and plug in t equals 0. Those expected values of x, x squared, x cubed are called moments. Why goes back to physics, though I don't know why physicists call them moments. They generate moments by taking derivatives and plugging in 0. So I differentiate this. I'll go ahead and put the numbers in front this time. The derivative of that term is itself. The derivative of this term you need to multiply by 2. Oh, it's not so surprising that this is coming out the way it is. 2 times 0.35 is 0.7. Then I'm using the chain rule. I need to multiply by an extra factor of 3 there. Yeah, it's, e to the 0 is 1. This is going to work out nice. I'm going to get 0.84 e to the 3t, and then multiply by 4 from the chain rule in the last term. When I differentiate, I get 0.60 times e to the 4t. Yeah, now plug in 0. The expected value of x is the derivative of the moment generating function evaluated at 0. You're going to get the same sum as before, 0.22 plus 0.70 plus 0.84 plus 0.60. Same answer as before, 2.36. Okay, so it's nice to see it work out nicely. You'd never guess this would work in the abstract, perhaps, but in discrete examples like this, especially where you've only got finitely many possibilities, it's easy to see how it works out and gives you the same answer. Number 8 is an abstract question. Assume you know some properties of the expected value operator, that it's linear. For example, e of x plus y is e of x plus e of y. The mean of x plus y is the sum of the means of x and y individually, and you can factor out constants. Goal is to show the details of calculations to confirm this formula here, which is also known as the variance of x. Where does this equality come from is the key. You need to also remember that these symbols are interchangeable. That's key to getting the final answer. It's just a matter of expansion and properties of the expectation operator. So I take the expected value of the random variable x minus its mean squared. I just expand the inside with the binomial formula, or you can think of it as the FOIL method, F-O-I-L. First times first is x times x is x squared. Outside times outside and inside times inside are both minus mu times x, so I get minus 2 mu x. And then last times last over here is mu squared. Linearity comes in right away. This is the expected value of a linear combination. That's the corresponding linear combination of the expected values, and I can factor out the minus 2 mu here because that's a constant. Like this. I could also factor out the mu squared there and be left with a 1 in there. So that's linearity of the expected value operator if you were asked to explain why. Now replace this with a mu. Remember, those are interchangeable. Replace this thing with mu squared because mu squared is a constant. You could think of it as a constant random variable that always takes the same value, mu squared. Its expected value certainly is mu squared. So I get the expected value of x squared minus 2 mu squared plus mu squared, which simplifies to the expected value of x squared minus mu squared. But mu, once again, is the expected value of x, so I get the final answer, the second moment, the expected value of x squared minus the expected value of x quantity squared. Okay, and that's the formula for the variance of x, though I didn't emphasize that in the problem statement. This is the definition of the variance. This is the formula that you often use. All right, last page, last couple problems. Second to last one looks kind of long. The very last one's not as long. Yeah, I think the second one is second to last is a little tricky here. Got to get your mind around it. You have just bought a car insurance policy through AARP, which is the American Association of Retired Persons. Yes, you're a new retiree. In the past, I'm not saying this is true in the future, you have averaged 3 car accidents over any 5-year period. Okay, it's just been your average, and you're trying to get some sort of 5-year policy, evidently. Not saying anything about how severe the accidents are, just saying there are 3 accidents. The insurance company makes you a provisional customer, saying we'll continue to offer you insurance maybe after the 5-year period. if you don't drive too badly. They're going to drop your coverage if you have 3 or more accidents during the 5-year period, the coming 5-year period. Part A, what is the probability that they will drop your coverage? Okay, let's go ahead and start that one. Then we'll look at part B. If X is the random variable, counting the number of accidents you have during the next 5-year period, the probability that we're after is that X is greater than or equal to 3. Okay, X is the number of accidents you have in the coming 5-year period. It's going to be easiest to do that using the complement rule and using the fact that X is discrete to say that this is true. X is discrete. So, and in fact, it can only take on whole number values. With whole number values, integer values, they're sometimes called. That allows us to say this. In general, with continuous random variables, you'd want to make these two numbers the same. So this is 1 minus probability that X is less than or equal to 2 is the sum of the probability that X is 0. You might have 0 accidents, or 1 accident, or 2 accidents. So by the summation rule, the addition rule for mutually exclusive events, it's that. What kind of distribution do we need, though? X, the number of accidents, is counting the number of accidents. What distribution does it have? This is a situation where you end up using something called a Poisson random variable, or maybe Poisson in French. Poisson random variable, and you need to know the PDF for it. It is a discrete random variable because it's counting the number of occurrences of an event, in this case having an accident. Its PDF, little f of little x, probability that capital X equals little x, turns out to be e to the negative power of the mean, in this case over this 5-year period. Let me write the mean. You could write it as negative mu power. It's also written commonly as negative lambda power. And in fact, for my students in our book, it's written as negative k power sometimes. Times lambda to the little x power. That's not x to the x, it's lambda to the x power, divided by little x factorial. So in the case of when little x is 0, it's going to be, and lambda is 3, e to the negative 3 times 3 to the 0 over 0 factorial, which is, of course, dividing by 1. 0 factorial is 1. When x is 1, I get e to the negative 3 times 3 to the first divided by 1 factorial. And when x is 2, I get e to the negative 3 times 3 to the second power divided by 2 factorial. Okay, 0 factorial is 1, 3 to the 0 is 1. This first term is e to the negative 3. E to the negative 3. And in fact, I could factor that out. I won't bother. 0.049787 is your probability of having 0 accidents in the next 5 years. If I multiply that by 3, because 1 factorial is 1, that's my probability of having 1 accident in the next 5 years. Poisson random variable often occurs when you're counting occurrences of an event over a given interval of time. It could be 1 year, it could be 2 years, it could be 5 years, it could be 10 minutes. Lots of different possibilities. And for this last one, I need to multiply by another factor of 3 and divide by a factor of 2. Looks to be 0.22404. We'll go ahead and approximate here. So add these numbers. Go ahead and round to say this to 0.423, say. So the final answer rounded would be 0.577. Okay. For the probability that they're going to drop your coverage, there's a pretty high chance. Part B is a continuous random variable. It's in this part and in the next problem where we're going to be the only places in this exam where we do continuous random variables. It'll be pretty heavily emphasized in exam 2. At the start of a 5-year period, what is the probability of your accident that your first accident will occur within the first year? Let W be the wait time for your first accident. That's a key here. W is a continuous random variable. It's the wait time until the first accident. It's not the count of something until the first something happens like it was for geometric. It's an amount of time which could be continuous. It could be a year, could be half a year, could be a third of a year, could be a 12th of a year, it could be a week, which would be a 52nd of a year. W can take on lots of different values. First accident was within the first year would be the probability that capital W is less than or equal to 1. Time is in years. Okay? That is going to be the integral from 0 to 1 of the PDF probability density function, and you really want a density in this case for an exponential random variable. I told my students it was exponential. It's got parameter beta, which is 1 over lambda, where lambda is the parameter from part A, and beta is the mean of this exponential random variable. Beta is 1 over lambda. That's going to be 1/3, 0.3 repeating. This is saying on average, if you get 3 accidents every 5 years, it's going to take you about 1/3 of a 5-year period to get to your first accident on average. Which doesn't, okay, I need to be careful here. Okay. Yeah, that means I made a mistake in my initial thinking about this, putting the 1 there and the 1 there. I'm taking time to be in really 5-year increments. Now, I wouldn't have to do that. I could convert it to yearly increments. But because it's 5-year increments, I really want to find the probability that it's 1/5 of a 5-year increment. Of a 5-year increment. That's going to be, i.e., 1 year. So it's tricky, and I purposely made it a little tricky to make sure people are on their toes, and it caught me off guard as well. Integrate from 0 to 1/5. 0.2 times 5 years would represent, again, 1 year. The PDF turns out to be 1 over beta times e to the negative, in this case, w over beta dw. If beta is 1/3, 1/3 of a 5-year period is how long it typically takes you to get your first accident. That would be in years. That would be 5/3 years. If beta is 1/3, then 1 over beta is going to be 3. So it looks like the integral from 0 to 1/5 of 3 e to the negative 3w dw. Okay. How big will this probability be? Probably not super big, but also not super small. Somewhere, some kind of moderate size, I'm guessing. Do the integral, you're going to get negative e to the negative 3w evaluated from 0 to 1/5. And that's going to be negative e to the negative 3/5 minus negative e to the 0. Carefully about your minus signs. That's 1 minus e to the negative 3/5. E to the negative 0.6. E to the negative 0.6. Take 1 minus that. Yeah, so it's not a super huge probability, but it's not super small either. About 0.451 would be the probability of being in an accident the first year, that the wait time of the first accident is 1 year or less, which is in 5-year increments, 1/5 of a 5-year increment or less. So yeah, you know, if my students put a 1 there and got the wrong answer, they'd still probably get most of the points because that was pretty tricky. Okay. Final problem. Let x be a random variable with density, and this is a true density because it's a continuous random variable. Little f of x is 1/16 x. X is over an interval of real numbers. This is a continuous random variable. And it's assumed that the density is also 0 otherwise, and that technicality is important sometimes. For little x between 2 and 6, find capital F of x, the CDF, When x is not between 2 and 6, f of x is 0 when x is less than 2, and capital F of x is 1 when x is greater than 6 for some technical reasons. We want to assume it's defined for all x. Part A is to find that. Let's go ahead and do that. Capital F is going to be an antiderivative, or if you prefer, antiderivative of little f. But not just any old antiderivative. It's a particular one. And if the left endpoint of the interval where little f becomes 0 is 2, for example, this is going to be the integral from that left endpoint, 2, to an arbitrary value of x of little f of, you should use a different variable name, doesn't matter, I'll call it t, dt. Okay? So we need to integrate from 2 to x. I'll go ahead and write it in here. 2 to x of 1/16 t dt. Okay? I want the variable to be the upper limit of the integral. This is going to be an antiderivative of little f by the fundamental theorem of calculus. And its value at 2 will be 0, which is what I want. That's going to be where it starts to go up in value, because that's where little f starts to have positive values. Integrate this, you're going to get 1/32 t squared from 2 to x. Looks like our CDF is x squared over 32 minus 4 over 32, or if you prefer, x squared minus 4 over all over 32. And of course, 4/32 does simplify to 1/8 as well. This is for x between 2 and 6. As a check that it equals 0 when x is 2. It does. You get 4 minus 4 is 0. Check that it equals 1 when x is 6, the right endpoint here of where little f was positive. 6 squared is 36. 36 minus 4 is 32. 32 divided by 32 is 1. Yes, this looks like it's right. So it's a particular antiderivative. You could just do an indefinite integral of little f and get a plus c. And then you would have to figure out what c is to make capital F of 2 to be 0, for example. And c would end up being negative 4/32, which is, again, negative 1/8. Part B. Find the probability that x is in the interval between 2 and 3, a continuous real number interval. You integrate the PDF, which by the fundamental theorem of calculus is equivalent to subtracting values of the CDF. So I can just do capital F of 3 minus capital F of 2 here. Okay? I could integrate the PDF from 2 to 3, but I don't have to. Might be easier since capital F has the extra subtraction thing in there, but let's just go ahead and do it this way. 3 squared is 9. 9 minus 4 over 32 is the value of capital F of 3. Capital F of 2 is 0. We already knew that. This is pretty easy. This is 5/32. 0.15625. Okay. Fairly small probability. The area under the PDF between 2 and 3, is a relatively small portion of the overall area under the graph. And you may want to check that the integral of this from 2 to 6 is 1, that it truly is a probability density function for a continuous random variable. Last thing to do, find the mean of x. Mu equals the expected value of x. And with continuous random variables, that means we need to integrate instead of sum. We're going to integrate over all x times the PDF. Over all x where little f is positive means we're going to ultimately integrate from 2 to 6 in this example of x times this, which will be 1/16 x squared, right? You integrate over the entire domain where little f is positive, x times little f. You don't do what we did in part A. And let's see. Do the integral now. This is going to be divided by 3, 1/48 x cubed from 2 to 6, from 2 to 6. That will be 6 cubed minus 2 cubed over 48. 6 cubed is 216. I should have known that. Minus 8 over 48 is 208 over 48. 104 over 24, which is 52 over 12, which is 26 over 6, which is 13 over 3. Okay. Looks like that's the simplest form for the answer. Of course, any of those is okay. 208 divided by 48 does indeed equal 13 thirds. 4.3 repeating is the mean. As an interpretation, if you were asked for that, that would be the center of mass, so to speak. 4 is right there. It's a little to the right of that. There's the mean. 4.3 repeating because the graph is higher over here, so the mass is weighted more to the right. Okay, and that's the last problem. Thanks for watching.